Aloha. For this problem, we're asked to think about blood flowing through a needle with a large volume of blood on top of it. And we're asked to calculate the viscosity of the blood. And the diameter of the needle, we're told, we'll label D, N, is 0.44 meters. And above the needle, there's a column of blood, which is a height of 1.40 meters. And we're told that the length of the needle, which I'll call L, is 3.8 centimeters. So it's good to just start out like writing down and giving a variable name to all the quantities that are given in the problem. And the volumetric flow rate, we're told, is what we'll call like capital V over T. That's 4.1 centimeters cubed per minute. So it's a volume over a time. And we want to find the quantity eta, which is the viscosity. And we can just look through the textbook in chapter 10 and find an equation that uses maybe all or at least some of these variables so that we can get an equation for the viscosity in terms of what we are told in the problem. And you'll probably come across Poiseuille's equation. So just like I shortened for Poiseuille's equation. And in that equation, Q is how we label the volumetric flow rate. And this equation came from experimental research. Fluid flow through a small tube like this needle. And we can just rearrange this equation to make this an equation for the viscosity eta. And we know that we don't have the radius, but we do have the diameter. So the radius is really the diameter of the needle over 2. And we could call this pressure difference delta P. So it looks like the only thing that we don't know is delta P. We know the diameter, we know the length of the needle, we're told Q, the flow rate. So we can just consider Bernoulli's equation because we have, pressure and potential energy coming into that. And we are also told the height of the blood above the needle in some other larger tube. So that makes us think about, gravitational potential energy. And that's where all that blood above the needle is what's creating this pressure difference. So you can just think about Bernoulli's equation, that the input pressure plus the input gravitational potential, and considering points where there's no kinetic term, so no flow happening, for the velocity 0, is equal to the same terms on the other side. And then we have P out minus P in. If we call this delta P, Y in. And really we're thinking here that the pressure difference here is coming about from the difference between these two heights. So it's really this distance h that we're told. So then we can plug this equation for this change in pressure coming from the change in height of the blood above it. And because both ends are open to the atmosphere, we know that we don't need to factor in adding atmospheric pressure to any side. because neither side is closed off. So we can then write this equation for eta as, and d squared over 2 squared, so that's pi over 4 delta P is, and this is rho is the density of blood, so that's a constant we can look up. So now we have an equation for the viscosity in terms of known variables. So we can just plug in those numbers and make sure we're using consistent units. So for the diameter of the needle, 0.44. I think I wrote down maybe the wrong number, but I think it's 0.40 millimeters instead of 0.44 meters. Okay, I just misread that. So if it's 0.40 millimeters, it's 0.40 10 to the minus 3 meters, and we were doing that to the 4th power. And the density of blood, you could find that in a table in chapter 10 in the textbook, Giancoli. You can look for this. Just up in the density of blood. For G, it's 9.8 meters per second squared. Acceleration due to gravity, and H was 1.4 meters. L is 3.8 centimeters, so that's 3.8 times 10 to the minus 2 meters. And we'll convert Q from what we're given, which is 4.1 centimeters cubed per minute. We know that in 1 minute, there's 60 seconds, so we're dividing by 60. And we know that in 1 centimeter is 10 to the minus 2 meters, so we have to cube that. So 10 to the minus 2 cubed would be 10 to the minus 6 centimeters cubed in 1 meter cubed. So then that's a unit conversion, so that we have this in terms of meters cubed per second. So we'll get an answer in SI units, 3.5 times 10 to the minus 3 Pascal seconds, where Pascal is defined as a newton per meter squared.